Hello there guys, and welcome back to another epic inexorable maths video. In this video we're deriving Euler's formula. Euler's formula, before we look at any of this stuff that I've written here about what we should know already, Euler's formula, I want to say this, it states simply that e to the I theta is identical to cos theta plus I sine theta, where I is the square root of minus 1 and theta is just an angle, or it's a number basically, any number that you want. Okay, so that's what it says. That's what we're trying to prove. That's what we're trying to get to right now. This, by the way, is an incredibly important formula. It's one of the most important formulas ever. So it's really, really useful. Okay, so to do this, we need to know just a few things. Really, it's only these. It's the idea that you can write sine x as this: x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial. It's all of the odd numbers, and there is a plus and a minus sign alternating between all of these things, okay? So it's the odd numbers. Cos x is the exact same, but with the even numbers. So it's x to the 0 over 0 factorial minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the, oh, that's supposed to be a 6, x to the 6 over 6 factorial, sorry. It's all of the even numbers, okay? All of the evens. And finally, e to the x can be written as simply 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4 over 4 factorial, x to the 5 over 5 factorial, etc. Goes on forever. All of them are infinite. But this, you can write all of these. Now, if you don't know where these come from, these are all called Maclaurin series expansions. And I have videos deriving all of them and the general formula for how you are supposed to do this. So I'll leave all of those things in the description below so you can check them out. If you're not happy with this, make sure that you are before we proceed here, because we're going to use them and we're going to rely on them a lot. Okay, so let's begin. Let's prove Euler's formula. Really, really cool stuff. First thing we're going to do is we're going to consider e to the x. We know what e to the x is. Remember, I've already written it down, but I'll write it down again. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And this just goes on forever. If I can count, x to the 4 over 4 factorial plus x to the 5 over 5 factorial plus x to the 6 over 6 factorial. And we'll go up to x to the 7, so x to the 7. I know my head's in the way right now, but x is 7 over 7 factorial. So this goes on again forever, but we are just going to write a finite number of terms, or else this video will be infinitely long, and I will not be able to upload it. So this is e to the x. It's this. This is the pattern for it, okay? And again, I've got a video deriving this. Now, if we consider replacing, because x is allowed to be any number that you want, any number. If we consider that x is actually a imaginary number, so let's say I times some real number theta, then we can replace the x with just I theta, and we're going to say no, x is going to be imaginary now. It's going to be explicitly imaginary. So if x is an imaginary number, the square root of minus 1 times theta, I times theta, what we get, literally just replacing x with I theta, we get e to the I theta is identical to 1 plus I theta plus I theta squared over 2 factorial, and I'll move up actually so you can see, so you can relate it to this here. So you can see what I'm doing. I'm just replacing all of the x's with I thetas. So we get an I theta cubed over 3 factorial. We get an I theta to the 4 over 4 factorial. We get maybe an I theta to the 5 over 5 factorial. And again, I'm just going to do a few more terms. I theta to the 6 over 6 factorial. That's good for now. Okay. And again, this goes on forever, but this is the general gist of it. We're replacing x with I theta, an imaginary number. So then what we want to do is we want to expand this. We want to simplify. So we expand all of this out. I theta then squared is equal to I squared theta squared over 2 factorial. I theta cubed is I cubed theta cubed over 3 factorial. We get I to the 4 theta to the 4 over 4 factorial. So I'm just expanding out the brackets. I'm getting rid of the brackets because we don't want to deal with them. And something really nice is actually going to happen if we get rid of them. And you'll see this in a second. Brilliant. And this goes on forever. This is the gist. This is still I theta, e to the I theta. Now, this means that we can continue to simplify this, and you will see something amazing. I promise. So the first term, 1 plus I theta. We need to think about powers of I right now. I squared, by definition, I squared is minus 1. So we get minus theta squared over 2 factorial. I cubed is just I squared times I again. So it's minus 1 times I, which gives you minus I. So I, or minus I, over times 3 times theta cubed over 3 factorial. I to the 4 is just minus I times I, which is minus 1, which basically gives you a plus 1. So I to the 4 is 1. Theta to the 4 over 4 factorial. I to the 5 is just I. So we get I theta to the 5 over 5 factorial. I to the 6 is minus 1. So we get minus theta to the 6 over 6 factorial. And this continues again forever. Now, what we're going to do is, because right now it just looks like a bit of a mess. It just looks like kind of a bunch of random terms. But what we're going to do is we're going to rewrite this, but we're going to rewrite the terms in a different order and do a little bit of factorizing, but not a lot. So we're going to write all of the real terms first. So basically all the terms that don't have an I in front of them, let's write those first. We're just going to swap the orders around. So 1 is real, so we'll put 1. Theta squared over 2 factorial, that's real. So minus theta squared over 2 factorial. Totally real. Plus theta to the 4 over 4 factorial, that's real. Theta to the 4 over 4 factorial. Minus theta to the 6 over 6 factorial. And again, this goes on forever, but look at the pattern. So it's 1 minus theta squared over 2 factorial plus theta to the 4 over 4. That looks a lot like cos. That's exactly cos theta, isn't it? Because again, this goes on forever, and we could say this. The next term is then theta to the 8 over 8 factorial. And it just goes on forever. So this is actually cos, but we'll replace it with cos in a second. So this is cos, and this comes from the series for cosine. Okay, the next thing is that we haven't written all the terms yet. We need to now write the other half of the terms that have i's in front of them. But what I shall do is I will factor the I out, and then we'll write them. Okay, so the first term is I theta, so we're going to write that as I outside the brackets times theta, that's I theta. The next term is minus I times theta cubed over 3 factorial, so this is minus theta cubed over 3 factorial because the I has been factored out. Then it's theta to the 5 over 5 factorial, so plus theta to the 5 over 5 factorial. And hold on a second, this is just the odd numbers. The next term here, if we went with another term, we used an I to the 7, etc., factored that out, we would end up with a minus theta to the 7 over 7 factorial. And this would also keep going on forever. But what is that? That's sine, isn't it? That's sine. So just if we go right back up to the top, we consult our formulas once again. Sine was, don't worry about the fact that it's an x and a theta, but it's the variable minus the variable cubed over 3 factorial plus the variable to the 5 over 5 factorial minus the variable to the 7 over 7 factorial. Hold on a second. That's just sine theta. That's sine theta. And cos theta is the same, but it's just with the even numbers. And it alternates between a plus and a minus sign. What we've got down here seems to be the exact same. So we can say that e to the I theta is identical to, well, this first bracket, it's just cos. So this is cos theta. And this second bracket is just sine. And it's being times by I, because it's I outside. But the second bracket is sine. So this is plus I sine theta. And this is Euler's formula. E to the I theta equals cos theta plus I sine theta. The really cool thing that you can do, what you can do with this, is you can show that e to the I pi plus 1 equals 0. So let's do that right now just for the fun of it. We use this formula for it. So theta again, theta can be any number. So let's let theta be pi for a second. Just as a fun exercise. We've already proved it, but just as a fun thing to do. We can say if theta is pi, then e to the I pi is equal to cos of pi plus I times sine of pi, right? Just replacing the thetas with pi. and then we get e to the I pi equals, and we just evaluate what cos of pi is. Remember, we're always in radians for these sorts of things. Cos of pi is -1, and sine of pi is 0. So it's I times 0. 0i. 0i is obviously just nothing, it's just 0 still. If you add 1 to both sides, because this is just equal to, would be 0 basically. If you add 1 to both sides, you get e to the I pi plus 1 equals 0. Just adding 1 to both sides. And also that's a really, really cool equation that you have right there. A really cool relationship between e, I, pi, 1 and 0. It's really, really cool. It's probably my favourite formula ever in facts, but that's how you prove that. But the real objective of this video is doing e to the I theta equals cos theta plus I sine theta. That is how you prove it. Hope that was helpful, guys, and I'll see you in the next video. Cheers.